first 5 topics, including the Z transform. Alright. So first of all, I will have you to review these topics. So remember last tutorial I described the Laplace transform. So why do we introduce Laplace transform? Remember, one advantage is it can simplify our calculation of the response, because in the complex Wick's domain, we just times the two transform together, and then using the inverse transform, so we can get the original response. So similarly, in Z transform, we also have the same reason. So we analyze the output in the Z domain. Z domain is the complex number here. So for the discrete one, so in time domain, we can calculate by the convolution. So it is like this. But in Z domains, we just first calculate the Z transform of the input signals and also the system signals, and then time them together. This is very easy. And then we using the mapping between the one mapping between the original signals and Z transform, so we can get the output in the time domain. So this is the reason. And another reason is, actually, if we can decompose the signals by the combination of exponential ways, it is Zn. So in the continuous times, we decompose by E S AK. So in discrete times, we want to decompose the original signals Sn by the combination of exponential components. So it has some advantage. So I'll give an example here. So assumes now the input is very easy, just say power to n. So using the convolution, we have the equation like this. This is summation of h and say n minus n. And then it's equal to say n so we see the input is exponential signals, and output is also exponential signals. The difference is it just times by some values, so it can change the amplitude and phase, right? So it means the output and input, they have the similar signals. The form are the similar. It is exponential signals. And we define this one by the Z transform. So if we can decompose any signals by the combination of exponential signals, that means for the output, we can always calculate the Z transform of the system, and then times by the input signals one by one, and then add them together, right? So let's motivate us to introduce the Z transform, because Z transform we according to the inverse transform. Okay, so like here. So in the inverse transform, it means the input signals, it can always be represented by the exponential forms, right? So so here integration, you can see like the summation here, right? So it means we can represent the original signals by the combination of exponential signals. And then that's the other reason why we introduce the Z transform in these topics. And for Z transform, we have two definitions. One is the bilateral definition. So the domain is from -infinity to infinity. And our mapping is the input is corresponding to one Z transform and also plus the region of convergence. Okay. And second one is the unilateral definition. So the difference is now the lower bound is from 0. So remember, in the continuous times from the Laplace transform, we from the unilateral definition, the lower bound is from 0 minus, right? So it can include the effect of initial conditions, right? But in this transform, we just it is from 0. So this is difference. And this is also one mapping. So it means so it helps. This can simplify the analysis of the causal systems and the causal signals because it always has the output after n equal to 0, right? So here in these topics we consider the unilateral definition here. So for one signals, it only has one. For one Z transform, it already corresponding to one input signal, one original signal here. And you need to know some basics signals in the Z transform. For example, the impulse signals is just one. And for delay signals, it's Z to power to the minus k here. And for the step functions, it is Z over Z minus 1. And if it comes by a delay, so you can consider this by un convoluted by delta n minus k. So we know for the convolution, the Z transform just time them together. So this corresponding to Z over Z minus 1, and this is corresponding to Z minus k. So just time them together, so we have this one. And also for the exponential signals, we need to remember it has the transform like this, Z over Z minus 1. So you need to keep remember this. All right. So also we need to know some important properties here. So the first one is the time delay. So we assume if the input is xn times by un, so the output is so the Z transform is xz here. That means if we introduce a time delay for the input signals, it just times by some Z minus k here. So this is corresponding to the convolution property and also delay signals. And second one is very important. So now, here, these two are different. But original signal, it is like here. In the original signal, these two are the same. But now, these two are different. So in the last topics, I have introduced how to change this part into the function of un minus k plus something. Remember, for example, n. So we want to express by n minus 2. How do we express it? Because un it has values when n is larger than 0, right? And n minus 2 it just have value when n is larger than 2. Okay, so this one it can express by this one plus 2 impulse here, right? So this 2 impulse here. So in this way, we can express this kind of signals by this form, right? So for this kind of signals, we have the convolution here. And I introduced one example to feel better understanding here. So for example, now k is equal to xn minus 2 un. Okay, so in this form, we want to have one component is we want to express this part by some x u minus 2 plus something, right? In this way, we have this part and time this part. So this is the time delay in terms of this one, just to delay. Okay, so we can write down by replace this part by u minus 2. So it should plus this 2, right? Okay, now we have 3 components. When you see some expression with one signals times by the impulse signals, you should remember it has this property. Right? Because this one, for these signals, it only has value when n is equal to k. It is equal to 1. When it is unequal to k, it is equal to 0. So this one, this function, it only has values when n is equal to k, right? So we have this part, and then you just write down this part, and then this is equal to. When n is equal to k, this one is xk. When n is not equal to k, it is 0. Right. So this part, we can know this actually is equal to x, n equal to 0, right? So it's minus 2. And this one, we should let n equal to 1, so it has value. 1 over 2, okay. So we have these 3 parts. So now it's easy. We have this one we can use in the time shifting property. For this one, we have the Zeitgeist form of the impulse signals, and this is the Zeitgeist form of the delays impulse signals, right? So this is equal to xj j minus 2. The second part, this is the constant value. And for this one, it corresponding to 1. And this one, this is a constant. And this one is equal it corresponding to j minus 1. Right. So this one is the Zeitgeist form of this function. So this is easy to understand. If you just remember the solutions, maybe sometimes you will get confused. So when you do something like this, for example, now it is plus, you can also use in a similar way, right? So it is plus. So this one, we should represent by n plus 2, and then minus right? So if it is plus 2, because you want to have this component, so this one, it should be equal to this one minus this 2, right? Okay, so this method you need to remember. Any problem about this one? The second property is the convolution. So this is why we introduce convolution. Zeitgeist form here, because the output actually is the convolution of the input and system response. So in this, to calculate, we can just calculate its Zeitgeist form and then using the inverse Zeitgeist form to find the original output. And this is to another property, the scaling. So this one is another exponential signals. so it corresponds to this form. And this one is also very, we can see very often. So for example, now you have the UN signals corresponding to J over J minus 1. So sometimes you will see some this kind of signals. So you can use in this property. It's always frequent to see. Okay. So the most important one, I think, is the first one, the time delay, especially for some simple component, for example, n minus 2 times by un. So you need to know how to calculate. All right. So the third component is the inverse Dirichlet form. So we can express the Dirichlet form by several components. One component has the form of ak j over j minus bk. So this one is corresponding to the original signal is ak bk n un. And the other one is the component of ck j minus k. So this one is corresponding to ck delta minus k. So in these topics, we want to decompose the inverse transform by this kind of forms, summation of this kind of forms. And then we can easily write down the inverse transform. All right? So an easy way is, first step, we need to write down by this way. We divide xj by j, and then we express the form by this kind of form. This one and this one. Sorry. It should be this one, this one. And then the second step is this part we times by j, so we have this form. Okay. And then for this form, we can easily find this inverse transform. So that's why, because we want this part j, because this form is j over j minus bk. So in the second step, we need to have the times by j. So in here it has j, and in this form we decompose it by the summation of this kind of, and then times by j we have this form. Any problem? So this is the normal way to calculate the inverse transform. And for the differential equations, we want to find the system output response. So the first step, we can use the time shift. And the problem here is how much time shift we need to perform. This is problem. So in later, I will tell you how to choose. And second one, you just apply the Dirichlet form. So you calculate the output by Dirichlet form. And then you use the inverse Dirichlet form to calculate the output. And last one is similar to the Laplace transform. We need to know how to represent the system, how to realize the system. So you can always represent it by these forms. And then you need to know how to realize the direct form 1, direct form 2, and transpose form. All right, so let's look at the first questions. So why do we introduce this form? I will introduce because it will simplify our calculation of the output response. You can calculate by this form, time them together, and then using the inverse transform. And there's some useful results. You need to know the some moment mapping. And also, this is time shift delay. If these two are different, you need to know how to calculate. All right. So now, several questions. First one. First one is we calculate unilateral Z transform. So the lower bound is from 0. Okay, so the input is 1 plus 3. So here we notice because this low bound is from 0, and we can see these 3 components. This one, it only has value when O is equal to -3. Right? It has value equal to 1. In other places, it's equal to 0. So it means from 0 to so write down the 3 components. So for these 3 components, the first one, we know only when N is equal to -3, it has value. In other places, it's equal to 0. So because this is from 0 to infinity, so it means this one is always 0. Right? So this part is equal to 0. In second part, we know this one, it only has value when N is equal to 0. In other places, equal to is equal to 0, right? So this one actually is equal to delta 0 times by J minus 0. Right? For the last part, so this one, it has U minus N, it has value equal to 1 when N is smaller than 0. In other places, is equal to 0, right? So because now the domain is from 0 to infinity, so it means it only has value when N is equal to 1. Because it is positive, this part is, this minus positive is negative, is equal to 0. So actually it only has one component. It's equal to, when this one is equal to 0, right? So this one is equal to 1. Okay, so then we add these 3 parts together. So this is the solution. So this problem, we need to know the property of this the impulse functions and step functions, and think about what's the domain here. Right. So for the problem C,